So welcome everyone to workshop 6, and this is the last workshop of this quarter. And we are going to talk about advanced math. Math is a very broad topic in ICPC, so we are only going to stick to exponentiation. At first, it's a raffle. And then we're going to have a quick review of binaries. Usually we count in decimal, also known as base 10. For example, 123 is 1 times 10 to 10 squared plus 2 times 10 plus 3. And we can apply the same logic to base 2. For example, 101 is 1 times 2 squared plus 0 times 2 plus 1 equals to 5. And we convert from decimal to binary by taking the modulo of 2 and divided by 2. For example, for 13 modulo 2 is 1, and 13 divided by 2 is 6. And 6 modulo 2 is 0, so the second digit is 0. And 3 modulo 2 is 1. And 1 modulo 2 is 1. And eventually we'll get 0. So the binary of 13 is 1101. And here's the pop quiz. Could anyone tell me what's the corresponding binary or decimals of these two numbers? The first one is 29 and the second one is 1010. And here's the code to convert the number from decimal to binary. When n is 0, of course, the binary is just 0. And when n is greater than 0, then we attach the modulo of 2 to the current string we have, to the front of the current string we have. And then we divide n by 2. And eventually we have s, which is the binary form in string of the number we have. Does anyone have any question to this code? Okay. And then we can move on to exponentiation. So what is a to the nth power where a and n are both positive integers? It is just multiply a for n times. And the code is pretty straightforward. It is just a while loop and repeat n times, and we multiply answer by a each time. And the time complexity is O(n). Now consider this question. Still calculate the a to the nth power, but here n can be as large as 10 to the 12th power. So you cannot apply the algorithm we have in the last slide because it is too slow. Usually, computer can do up to 10 to the 9th calculation in 1 second, which is the time limit of most common competitive programming problems. So if you use the O(n) algorithms, then this problem your program may run up to 100 seconds. So we need to have some more efficient algorithms. And before that, consider this question. What is the minimum number of multiplication you need for 3 to the 10th power? Or can anyone tell me if there is a number of multiplication you need to calculate 3 to the 10th power that is less than 9? Okay. So instead of multiply 3 fruitly for 10 times, we can multiply 5, 3 together, and then we square the product. And then there are only 5 multiplication involved. And an even faster approach is that we can multiply 3 and get a squared, and then we square the square. And then we multiply 3 to the square again, and then we square the product. And then there are only 4 multiplications, but we still get 3 to the 10th power. Let's look at another example. How do we calculate 3 to the 17th power efficiently? First, we write 17 equals to 8 times 2 plus 1. And here, plus 1 in the exponent means that we multiply the powers by 3. And times 2 means that we square the powers. So there are only 2 multiplications involved. Then we only need to consider how to calculate 3 to the 8th power. And we know that a equals to 4 times 2. So here's another multiplication. And then we consider how to get 3 to the 4th power, which is 3 squared times 2. So in conclusion, we have this, and there are only 1, 2, 3, 4, 5 multiplications. So we can generalize this in a more systematic way. That is, if n is positive odd, then we split a to the nth power into a to the n minus 1 power times a. And when a is positive even number, then we split a to the nth power into a to the half n power and then squared it. And when n is 0, of course, it is 1. Does anyone have any questions here? Yes.
Are you, like, because multiplication itself is going to get longer, it's going to take more time, the numbers going to take, or are you actually fitting in time?
I think our numbers are not that large. It's like, I mean, if it is as large as you have to use fast Fourier transform, then that is too large for this part. And here we implement that exponentiation recursively. When n is 1, we just return 1, and when n is odd, we calculate a to the n minus 1 power and multiply n. And otherwise, we calculate a to the half n power and then we square it. Notice that we have to use this auxiliary variable here. Otherwise, we are not calculating less amounts. And the time complexity here is O log n. You may notice that we are not always decreasing n by dividing it by 2. Like when n is odd, we only minus 1 to it. However, the impact is too little comparing to how efficient we are when dividing 2, so we can, not very rigorously, we can ignore this. Does anyone have any questions? Okay, so we just introduced how to calculate fast exponentiation recursively, but usually we prefer non-recursive algorithm because recursion can take a lot of stack space sometimes. Then are there any better ways? And the key is that we need to use a binary to solve that. Now get back to 3 to the 10th power, how to calculate it with binary. First, we write 10 in binary, which is 1010, and which is equals to 1000 plus 10. And then we split it into 2 powers product, and then we write it in decimal. So why do we need that? That is, if we need to calculate the power of a to the nth power, then we can split n into powers of 2. So to do that, we can scan n in binary from right to left, and if the case digits of n in binary is 1 or non-zero, then we multiply a to the 2 to the case power to our answer. And otherwise, we just keep scanning to the left until we meet a non-zero digit. So let's look at another example. Oh, wait, what happened? For example, 5 to the 13th power. We first write 13 in binary, which is 1101, and then we write them into a sum of 1 and several 0. And then we split it into some powers and write them in decimal, which is 5 to the 2 to the 3rd power times 5 to the 2 to the 2nd power times 5. And to implement it, we write a while loop here, and n modulo 2 is the current digit. So n modulo 2 equals to 1 means that our current digit is non-zero. So we need to update our answer. And otherwise, we need to update our a to change it from a to the 2 to the k to a to the 2 to the k plus 1. And after that, we move 1 digit leftward, which is n divided 2. And for these 2 lines, we can just write a updated to a times a, because you square a to the 2 to the k's power, it is equivalent to changing it into a to the 2 to the k plus 1 power. And then you multiply answer by a. Does anyone have any question here? Okay, so we have digital worksheets this time, and you can see the code of fast exponentiation and the matrix exponentiation later on this worksheet. And it is almost completed, and if you fill up it, you can get raffle tickets. And let's see an example problem. This is a link to our contest this time. And does anyone have the link now? Okay, so let's move on. Let's have 1 or 2 minutes to read this problem. So the problem itself is pretty straightforward. It gives you several arithmetic expression that is a plus b or a times b or a to the b's power, and you need to calculate that and print the last 4 digits of them. So to do that, we just keep reading in the form integer operator integer. And notice that you cannot use integer, and you have to use long integer or unsigned int, because the range of integer is less than 2 to the 31st power, but our input range can be up to 2 to the 32nd power. And here's the code of the main function. Can anyone tell me what is the mode here? Hint, we need to output the last 4 digits of it. Okay, it is 10 to the 10,000, because if you mode 10,000, then it is automatically give you the last 4 digits of a number. And also here's the problem about the code in this line, because we have to modulo before and after multiplication. Because even though we use long to store a and b, but their products are still going to overflow the range of long. And we have to modulo a and b before calculating their product. And then here's the code of the fast exponentiation function. It is almost the same as the previous code, except for we add modulo arithmetic here. Does anyone have any question? Okay. Then here's a bonus question. How to calculate the sum of this series? Notice that n can be as large as 10 to the 9th power. So you cannot calculate each term with fast exponentiation and add them together. Well, a way is to use geometric series. Notice that this sum is on the left-hand side is a geometric series. So use that we can get it is equals to a to the n plus 1 power minus 1 and divide a minus 1. Now from this question we have, what if the a are matrices instead of numbers? And n can be still as large as 10 to the 9th power. And I here is a 5 by 5 identity matrix. Of course, we can still use geometric series. And we get a to the n plus 1 power minus I n times a minus I inverse. Now, the question is, can we apply fast exponentiation to matrices? And of course, yes. Is anyone familiar with matrix multiplication? If you are, please raise your hand, because if everyone are familiar with it, then I'll just skip this part. Okay, then I'll still go through this part. So we have A and B two matrices where A has n rows and m columns, and B has m rows and k columns. And the rule to calculate the entry at the ith row jth column is by this formula here. It may look a bit abstract, so we are going to demonstrate how it works. So first, for example, we need to calculate C11. Then we take the first row of A and the first column of B. And then we pick the first entry in these two lines. That is A11 and B11, and we multiply them together. And then we pick the second entry, that is A12 and B21, and we multiply them together again. And then we add A13 times B31. And then we eventually get to the mth entry, that is A1m times B1, BM1. And similarly, we can do this process for C21. And we need to take the second row of A and the first column of B. And eventually we get to CNK, that is the nth row of A and kth column of B. Here's a quick question. What is the product of these two matrices? Yeah, so for the C11, we have we take the first row and the first column, which is 1. And for C12, we take the first row and second column, which is 4. And then C13 is also 4. And C21 is 4. And C22 is 1. And C23 is 4. And then 4, 4, 1. So here's a code of matrix multiplication. It is just 3 loops. The first loop is enumerating the ith row of C or ith row of A. And the second loop is enumerating the jth column of C or jth column of B. And the third loop is enumerating the entries in each line. And then we add the product together to get Cij. Does anyone have any question here? Okay. Oh, it's also on the worksheet. And so we can, by the rules of matrix multiplication, we can multiply two matrices A and B if and only if the number of columns of A equals to the number of columns of B, the number of rows of B. And also their product has n rows and t columns. And as for matrix exponentiation particularly, we only cares about square matrix A, because otherwise we cannot multiply A to itself. And given an n by n matrix A and integer k, how to calculate A to the kth power? Actually, we only need to change a few things about the ordinary factor exponentiation. The first thing is to change all scalar multiplication to matrix multiplication. And the second thing is to change multiplicative identity to identity matrix. So for identity matrix, it is an n by n square matrix, and the diagonal entries are all 1 and the rest are all 0. And one may verify that for all n by n matrix A, AI equals to IA equals to A. So we call it identity matrix because it plays the role of identity in matrix multiplication as one in scalar multiplication. And here's the incomplete code of matrix exponentiation. Suppose we already have the class matrix, and suppose we already define what is I. And here we initialize the answer matrix to be identity matrix. And this is just the ordinary structure of fast exponentiation. And here the star here is the matrix multiplication. And then we are going to go through how to define the matrix class. Here, at first, we initialize all matrices as 0 matrix. And the build function here is to generate the identity matrix. And the operator here is to overload the ordinary multiplication. And the code inside this, inside it is exactly the same as our previous matrix multiplication sites. And there's too little space on this slide, so I omitted. But you can see it on the worksheet. Does anyone have any question to this slide? I guess it is not included in CS32. Or are there anything confusing on this slide? Yes.
The reason why we don't use Strassen's theorem to do matrix exponentiation is because like recursion takes up too much storage.
You use Strassen to do matrix multiplication?
Yeah.
Oh, I think I'm just too lazy to write that. And also, if you do Strassen multiplication for n times, it is still much lower than this, right? Because it is decreasing the efficiency of matrix multiplication from n3 to 2 point something. But here we need to do matrix multiplication for k times, and k may be very large. So if you only decrease the efficiency of matrix multiplication and k is still large, then it's still time limits exceeded. And the question is, so what? I mean, we develop such techniques is not only for calculate some useless enormous matrix powers. And then we are going to talk about a very interesting application of it, which is about recursion. If you are not here previous workshops, then we're not going to go deep into recursion itself. Recurrence is just a concept that It's a relationship that each current terms is determined by the previous terms. And we have a basic term, so we can calculate each term recursively. And suppose we have such a recurrence relationship, and we need to solve Fn. How can we connect this with matrices? So for this recurrence formula, if we want to do matrix exponentiation to it, then we want to obtain a matrix A such that we multiply matrix A to some matrix that contains Fn minus 1 is equivalent to do one recurrence to Fn minus 1. Then we want to do this because instead of doing recursion for n times, we can calculate A to the nth power by matrix fast exponentiation, and then we multiply the matrix power to F0. Then we reduce the time complexity from O(n) to O log n. And the cost of matrix multiplication here is omitted because usually the matrices are small. So how to find such matrix A? And we notice that Fn equals to this by our recurrence formula directly. And then we have this. So Fn1 equals to AB01 to the nth power multiply F01. Actually finding the recurrence matrix for recurrence relationship is a bit technical sometimes, and it is not that easy to find the general form of it. So we are not going to go that deep, but we are going to explain more and hope it can give you some intuition towards it. Now take a look at this. Take a look at the matrix multiplication. Here, these are two column matrices. And the B matrix here describe our current state, and the rightmost matrix here describes the state after one recursion. And what does this tell us? So every entry in the current state, as we can see, B1 to Bn, appears in this matrix. So every entry in the current state may all possibly affect the final state. So we can view Vi as our current state, including constants, and Ai as some coefficients. And look back to our previous example here. We can see that Fn minus 1 and B are the only terms that affect Fn. So we let the two entries in our column matrices be Fn minus 1 and 1. And then we solve for A2 by 2 by this relationship, which is a system of linear equations here. And then eventually we get AB01. Does anyone have any question here? So generally, if the recursion is in this form, that is Fn equals to some constant times the previous terms, then you can find the recurrence formula in this way. We are going to talk about some more concrete examples in the following parts, but now let's take a look at these bonus question we had. Now we already know how to calculate matrix power. So now the only problem here is how to calculate this inverse. You may already know how to calculate the inverse by hand, but it is not that easy to code it, at least not in today's agenda. And here's a hint. You can actually find the recurrence relationship of the sum Sn defined here. Does anyone notice any recursion here? We can define S0 to be 1 and Sn equals to Asn minus 1 plus I, where I is identity matrix. And this is exactly correspond to our sum here. And then you may notice that this is very similar to the previous example we had, that is the Afn minus 1 plus B example, except for here, they're all matrices instead of constants. And similarly, we can solve for the matrix here. But the entries here are matrices instead of constants. But we've already overloaded matrix multiplication, so we can just treat them as numbers and the implementation won't be too bad. Okay, then we are going to look at some example.
All right, hopefully everyone had a bit of time to look at the problem statement. I'll summarize it for you. So essentially, we start with one pair of porpoises, and each year the following two events happen. All parents that were around last year, they stay, and all pairs that were around 2 years ago have a pair of new babies. The task of the problem is to find how many pairs of porpoises will there be after n years, where n is the input. So there is this pattern, and we can summarize it basically by saying that the number of porpoises this year is the sum of the number of porpoises 1 year before plus the number of porpoises 2 years before. So can someone tell me if they can say what kind of pattern, which sequence has the similar pattern, where the current number is the sum of two previous numbers? Anyone?
Fibonacci.
Right. So basically, it's essentially a Fibonacci sequence, because in Fibonacci sequence, you start with 0, 1, and then every next number is the sum of two previous numbers. So in a nutshell, our task is to calculate the nth Fibonacci number. And this sounds easy because we actually did that. If you were here a couple of weeks ago when we were covering dynamic programming, there is a simple solution to this problem using recursion and dynamic programming. However, there is one certain aspect of the problem that makes it very different from the original problem statement. And essentially, the number n can get up to 2 to the power of 48, which is a terribly huge number. And moreover, we need to process up to 100 such requests. So we need to solve 100 such problems, which makes the number of computations even larger. Our dynamic programming algorithm is O of n. And as Charlotte mentioned, as you know, we can only, we'll exceed time limit if we perform more than 10 million or so operations. And this is clearly more than 10 million operations. So all in all, our DP algorithm will be very slow, and we need something faster than that. And we can actually use matrix exponentiation here. So let's try to build the recurrence matrix for that. Here, you can see the simple recurrence relation for Fibonacci sequence, where Fn is Fn minus 1 plus Fn minus 2. And since this recurrence relation has two terms, we're looking for a matrix of dimensions 2 by 1. So now, if we consider two matrices that represent our current and previous state, Fn, Fn minus 1, and Fn minus 1, Fn minus 2, there is not a very difficult, it's easy to observe this relation between those two matrices. We see that if you multiply matrix Fn minus 1, Fn minus 2 by matrix 1, 1, 1, 0, we'll actually get the exact same matrix we have now, Fn, Fn minus 1. So does anyone have any questions so far about how we got to this step? And why this is correct relation? So essentially, we can perform this kind of operation many more times, so we can perform it again and again. And eventually, we'll get on the right the product of this matrix 1, 1, 1, 0 to the power of n minus 1 times the matrix that represents our base case as the number n becomes smaller and smaller. And as we get the base case, we know numbers for the base case, basically f1 and f0. So this is what I just said. This is the relation that we'll get eventually. One thing to pay attention here is the power n minus 1. It might not be immediately obvious why we actually have power n minus 1 and not n plus 1 or something like that. And unfortunately, I cannot think of any easy solution to that, how to come up with such number. So essentially, you just need to try to substitute some small numbers instead of n and see if it works. So we can do that right now. Let's say we substitute n equals 2. So we substitute 2 here, and then on the right, we get multiplication of 1, 1, 1, 0 times matrix 1, 0. So the result would be matrix. First entry would be 1 times 1 plus 1 times 0, which is 1, and then again 1 times 1 plus 0 times 0, which is 1 again. And that's what we expected, because the result would be f2, f1, and both of them are indeed 1. And you can actually play around and check out different values of n and make sure that this formula actually works. So in our solution idea, we can calculate the n minus first power of this 2 by 2 recurrence matrix using fast matrix exponentiation. So imagine we get matrix Mn with the following set of entries. It's going to be 2 by 2 matrix after the exponentiation. Can someone tell me what would be the output of our program? So we are trying to find the number Fn. So which, let's say, entry should I print out here? One of these 4 as the result of my problem. Essentially, this is what we get after performing this computation, after performing like this first part of the computation. All you need to do is multiply by matrix 1, 0, and then see where Fn is. So any suggestions? It's one of those 4. Which one? That's close. That's it's close. No, it's not 821. Any other suggestion? No, there's 3 left. Yes, it's A11. Exactly. Basically, it's entry A11, and we can see that by performing that multiplication. So we get A11 and A12. So we get this matrix and multiply it by 1, 0. So on the top, we would get A11 times 1 plus A12 times 0. So we only get A11, and that's the term that should represent Fn. So that's why we output it. And one more thing we should remember is that this problem has several requests. So we first read in the number of requests, and then we need to repeat this process for different inputs p times. All right. Does anyone have any questions about the solution idea that I covered so far? Is it clear how we get to this formula and then find the answer? Okay, so let's try to code this up. This is a template, and most of this code already appeared on the slides. And there is only a small chunk of the code that we actually need to write to solve this particular problem. Everything else is reusable. That's why it's a template. There is a lot of code here, so let's try to break it apart and look at it one by one. So on the left, we see that there is some global variables are essentially the modulus. In the problem statement, there was a condition that we need to output the value modulo 10 to the power of 9. That's why we have this modulo. And then we have a structure matrix 2 and its methods. And then we have two more functions. So let's first consider the structure, struct matrix. So struct matrix has 3 parts in it. First is the data variable, which is a 2x2 two-dimensional array of integers, which will hold our data values. It has a constructor, which zeroes out the matrix. So all the values initially are 0. And finally, it has matrix multiplication operator. It has it redefines multiplication operator, and which performs matrix multiplication that we talked about before. If you haven't seen this notation before, don't worry. So what it does is we can see what it does by looking at a particular example. So let's say we consider this equation A equals B star C, and let's say all of the variables are matrices. So what this will do, the right side will do, is it will invoke this method on matrix B, where the other input variable will be equal to C. And that's how it will perform multiplication of matrices 2 and B and output the product. So result of the right side of the equation would be B times C in terms of matrices, and it will store it in variable A. And the code is exactly the same as it was when we talked about regular matrix multiplication. All right, so one more piece of code that we had on the slide was fast matrix exponentiation function. And there's no change here. Essentially, this function takes in one matrix and the number, the power that we need to take it to, and then it returns another matrix, basically the result of the operation. It's exactly the same that the code that we showed on a couple of slides before. Does anyone have any questions about these 2 pieces of code so far? All right, let's actually move on to the code that we need to write by our own. This is the main function. We read in one number, and this is the number of requests, and we need to perform these following operations p times. Let's say take around 5 minutes to think about which lines of code you would write instead of to-do statements. Essentially, it's the same as the solution idea process, but in code this time. I'll leave this slide up, and let's think about it for 4 or 5 minutes. All right, does anyone need more time to think about it? I'll try to go over the solution. It's pretty short. So here is the full solution code. Essentially, we read in 2 numbers specified by the problem statement input. The first number is just the number of the test case, and then the second is the power that we need. The second is the number, Fibonacci number that we need to find. We initialize matrix M, and we set its values to our recurrence matrix 1, 1, 1, 0. Then we just simply take it to the power n minus 1 after using the puff function for fast matrix exponentiation. And finally, we output the first leftmost and topmost entry of that matrix. Does anyone have any questions about this part of code or anything at all related to this problem? If not, we'll move on to our next example problem, which will be very similar to what we just talked about. It's not on Cadis, it's on Codeforces, which is a different competitive programming platform that also hosts a lot of competitions and trainings. If you want, you can follow the problem link, or I also have the problem statement up here. It's very short. Let's take just like 1 minute to read these few lines, try to understand what the problem is talking about. All right, let me quickly summarize the problem. So we have Limak, and initially Limak is happy. Limak can be either sad or happy. Initially, he's happy. He reads a string of uppercase English alphabet characters, and each character can somehow impact his mood or can actually do nothing. So, for example, letters S and D will make him, reading letters S and D will make him sad. Reading letter H will make him happy. Reading vowels will flip his mood. So if he was happy, he will become sad. If he was sad, he will become happy. And then all other letters simply do nothing. The task of the problem is, given the string length, we need to find the number of such strings of that length that will make Limak happy after reading them. So this, does anyone have any questions about the task? The problem statement? So it may sound a bit complicated. So let's take a look at a couple of examples to understand what's going on here. So this first example, let's actually consider a particular string. That's not what the problem statement asks, but this will help us to understand what's happening with the mood flings of Limak. So we consider this particular string, assuming that he's happy initially. Can someone tell me what will reading this string do to his mood? Will he be happy or sad after reading this string? So remember, S and D make him sad, H makes him happy, vowels flip his mood, and all other letters do nothing. Yes, so he starts off happy. Yes, the question is like, will he be happy or sad after reading all these characters?
Oh, wait,
Sad? Yes, that's correct. This task actually is a bit tricky because like there is a lot of things to consider, but actually if you look at the last part of the string, the Limak will become sad after reading letter D, so it doesn't really matter what's happening before. I'll just quickly go over what's happening so we understand how letters affect his mood. So he's happy initially, he reads letter A, so he becomes sad. Letter B does nothing. Letter S makes him sad again. Letter R does nothing. H makes him happy. O flips him mood, so he's sad. S and D keep him sad. A flips his mood, so he becomes happy. W does nothing. And E flips his mood again, so he's sad now. And F does nothing. So eventually he's sad. I hope this is helpful to understand how the process of reading works and how the process of flipping his mood works. But let's actually go back to what the problem is actually asking about. So can someone explain this example input? What's happening here? Basically, the input equals 1. So we need to consider strings of length 1. And the output is 19. Basically, the number of strings of length 1 that make him stay happy. Can someone explain why is it 19? Considering that this is the distribution of what different letters can do to his mood. 2, 1, 5, 18. Yes, essentially, because since the length of the string is 1, it's just one character, and the problem asks what characters will make him happy after reading them, or will not change his mood since he's happy already. And that's either H that will make him happy anyways, or all other letters that will do nothing to his mood. So it's 1 plus 18, which is 19, and essentially these are all valid answers to this problem, but we only need to input the number. All right, so far, does everyone understand what the problem is asking about? Okay, so let's try to come up with a solution to this problem. So our first attempt would be dynamic programming. This workshop is not in dynamic programming, so I'll just briefly mention that there is O of N solution using DP. I put out some hints on the slide. I'll not go in detail what's happening here, but just letting you know that there is a linear dynamic programming solution. However, as always, we can optimize it using matrix exponentiation. And in this case, moreover, n is very large. I think it can get all the way up to 10 to the power of 12 or something. It's stated in the problem statement. So dynamic programming would be useful if n was smaller. But in this case, we actually can do better using matrix exponentiation. So let's first consider a simple example and visualize the problem. We will use vertices to indicate the two moods that lemma can have, happy and sad. And then the edges will have number of ways to move from one state to another. So first we consider a string of length 1 character. So we have two columns. First column is the mood of the lemma right before reading the character. So it's 0 characters read. And then this column is right after reading 1 character. So it's 1 character read. And he can be either happy or sad. So first of all, can someone tell me how many ways are there to get from H0, this box, to H1? Anyone?
No idea.
Well, it's actually very similar. It's based on the example that we just talked about. So it's very similar to the answer to the previous problem. So what it's asking about is how many strings of length 1, so how many characters will make him stay happy after reading them. And it's essentially 19. That's what we saw right before. Interestingly, we can actually do the same process with 3 other arrows, with 3 other transitions from sad to sad, sad to happy, and happy to sad, by doing the similar operations. And we can calculate that essentially those numbers are 7, 6, and 20. You can go back to that first chart with the number of characters and what they do to lemma and actually see that those are just combinations or just the sums of different parts of those of the problem statement. You might be wondering why we are when considering lemma in a sad state initially, and why do we care about this sad state? Why do we care about these transitions? So here we generalize the problem, and generalizing the problem sometimes can be very helpful to solve a particular problem. And this is an example of that. So if we find a solution of how many ways are there to get from sad to sad, sad to happy, happy to sad, and happy to happy, we are looking for 4 numbers instead of 1, but we'll see how that helps us to solve a bigger problem when we have many more characters. And of course, after all, we'll find the value for happy to happy, so there's nothing to worry. We'll still solve our problem anyways. So are there any questions about this first step here with 1 character? If not, let's just focus on these 4 numbers for now, 19, 7, 6, and 20, and put them in a matrix. I know it might be unintuitive, but let's just keep it in the back of our minds for now. This is essentially going to be our recurrence matrix, and we will see that in a bit. To see that, let's add 1 more character to our diagram. So now we have 2 characters, and the second part of the diagram essentially looks the same as the first part. So all those transitions have the same number of ways. Now the question is, how many ways are there to get from H0, this state, to H2, second state? Does anyone have any suggestions? Right. So you start here, and then you can consider all paths that can lead to H2. And essentially, there are 2 of them. First path you can take is you get from H0 to H1 and then to H2, which means that you were happy initially, you read 1 character, you're still happy, and then you read second character and you're still happy. So this is going to be 19 times 19 possible 2 character strings. And then the second path you can take is after reading one character, you become sad, but after reading the second character, you become happy again. And this is going to be 7 times 6 number. This is going to have 7 times 6, which is 42 number of 2-character strings. And then we just sum up those two numbers and we come up with 403. Essentially, we can do the same exact thing with 3 other values when we get from sad to happy, happy to sad, and sad to sad, and come up with those other 3 numbers. Are there any questions why this formula is correct? How we get from 1 character to 2 characters? How we expand this problem? So if not, let's actually take a look at our matrix that we wrote back a couple of slides ago. We can keep these values that we got on the previous slides in a matrix as well, in the following way. And one interesting observation that one can make is that the matrix that we get for 2 characters is actually the square of the original matrix that we got for 1 character. And it's true, and it's not difficult to observe that we can get the required answer with n characters by taking matrix M to the power of n. Each time we multiply by matrix 19, 7, 6, 20, we add 1 more character. So essentially, if we take this matrix to power n, we'll consider all strings of length n. So this leads us to a pretty straightforward solution idea. We read in the value n, the length of the string we are considering. We create matrix M with initial values 19, 7, 6, 20. And as we are taking it to power n using fast matrix exponentiation, each step, entries in matrix M to the power of k will correspond to number of ways to get from initial state that Limak has, happy, sad, to state that he has after reading first k characters of the string. When we reach to n, we will essentially complete our task and consider the number of all strings of length n. Now the question is, again, the same question as we had in the previous problem. Since we are getting 4 numbers and not 1, and we only need to output 1 number, can someone tell me which value we need to output after we get m to the power of n? Which value in that matrix would correspond to happy transition? And remember that this is what we had initially. Yeah, I guess this slide makes it obvious that basically we need to write out the topmost, leftmost entry, basically entry 0, 0, because it corresponded, because that entry corresponded to happy transition, our original recurrence matrix, and that condition will hold even after we take that matrix to the power of n. So all we do is output the 0, 0's entry. Does anyone have any questions about the solution idea? So if not, I guess we're a bit short on time, so I'll go over the solution. It's largely the same as the solution to the previous problem. So as you can see, all this part of code is copied directly from the previous solution. We have struct matrix with 2 by 2. We have function pop, and the only small minor change is that the module here is 10 to the power of 9 plus 7, not 10 to the power of 9, just because of it's mentioned in the problem statement. So again, the only difference is the function main, and essentially we need to initialize matrix M, take it to power n, and output the first entry. And that's exactly what we do. We read in number n, we initialize my matrix M, we write in values 19, 7, 6, 20, take it to the power of n, and output the first entry. That's the entire solution. Does anyone have any questions about this problem? Or the code for this problem?